One day, the universe as we know it will end. And for nearly 30 years, scientists have agreed on how that ending will play itself out. Over trillions of years, galaxies will drift farther apart, stars will burn out and die, black holes will slowly evaporate, until all that's left is an infinite expanse of cold, dark, empty space. This is the Big Freeze, powered by dark energy, the most likely fate for everything that exists. Or so we thought. Because in 2024, something changed. New findings from the Dark Energy Spectroscopic Instrument, DESI, revealed something shocking. Dark energy's grip on our universe might be weakening. And if that's true, if the cosmic engine powering our universe is running out of steam, then the very fate of the universe hangs in the balance. Welcome back to the Curiosity Beast, where we explore the mysteries that define our existence. This is part one of our journey into dark energy and the end of everything. Today we're uncovering how scientists discovered that the universe is accelerating toward its doom, and why that discovery won the Nobel Prize. In part two, we'll reveal what's happening right now, why dark energy might be changing, and what that means for the ultimate fate of the cosmos. Let's start at the beginning. 1998, the year everything changed. By 1998, we already knew the universe was expanding. Edwin Hubble had proven that back in 1929 by observing that distant galaxies were moving away from us. The farther away they were, the faster they were receding. But scientists still had a fundamental question. How fast is the universe expanding? And more importantly, is that expansion slowing down? Logically, it seemed like it should be. Gravity pulls everything together, so over time the expansion should slow, maybe even reverse, leading to a big crunch where everything collapses back into a single point. To answer this question, astronomers needed to measure something called the Hubble constant, a value representing the speed at which the universe is expanding right now. And the best way to measure that? Type 1a supernovae. These are massive stellar explosions. And they're perfect for this kind of measurement because they all explode in basically the same way. Thermonuclear detonations of white dwarf stars in binary systems, which means we know exactly how bright they should be. By comparing their true brightness to how dim they appear from Earth, we can calculate their distance. Then, by measuring their redshift, how much their light has been stretched during its journey, we can determine how fast they're moving away from us. It's elegant, simple. And in 1998, two independent teams set out to do exactly this. Teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees observed more than 50 Type 1a supernovae, and what they found was completely unexpected. The supernovae were dimmer than they should be, which meant they were farther away than predicted. Drop a comment. Did you know about this 1998 discovery? Let me know if you've heard of dark energy before. Now, that might not sound like a big deal, but the implications were staggering. If the supernovae were farther away than expected, it meant the universe wasn't just expanding. It was accelerating. Think about that. The expansion of the universe is speeding up, not slowing down. Speeding up. It's like throwing a ball into the air and watching it accelerate upward instead of falling back down. It defies intuition. To visualize this, imagine an uninflated balloon with dots drawn on it. As you blow air into the balloon, the dots move farther apart. Not because they're moving through space, but because the space itself is expanding. That's what's happening to galaxies. The space between them is stretching. And not just stretching, accelerating. But here's the problem. What's causing this acceleration? Gravity pulls things together, so something else must be pushing them apart, some unknown force. Something we'd never detected before. And because we didn't know what it was, scientists gave it a name. Dark energy. Now the name is frustrating, because dark doesn't mean it's evil or shadowy, it just means we don't understand it. We can't see it, we can't measure it directly. We only know it exists because of its effects. Most scientists think dark energy is a property of empty space itself, the energy of the vacuum. Others think it might be some kind of energy field pervading the universe, or cosmic strings, defects in the fabric of space-time. And some scientists think it's not a new force at all. They think it's a flaw in our understanding of general relativity on cosmic scales, that we're just bad at calculating gravity over huge distances. But whatever it is, dark energy became the foundation of a new model of cosmology, the lambda cold dark matter model, or lambda CDM. Lambda is a Greek letter representing the cosmological constant, a mathematical parameter for dark energy first proposed by Einstein. And CDM stands for cold dark matter. This became the standard model of cosmology, the most widely accepted framework for understanding everything from the Big Bang to the ultimate fate of the universe. And here's where things get wild. According to this model, 68% of the universe is dark energy, 27% is dark matter, the invisible stuff that holds galaxies together through gravity, and only 5% is normal matter. Stars, planets, you, me, everything we can see. Let that sink in. 68% of the universe is something we don't understand. And we've been basing all our predictions about the future on the assumption that this dark energy is constant, that it never changes. And if dark energy is constant, then the universe's fate is sealed. The Big Freeze. Here's how it works. Dark energy pushes galaxies apart, and as the universe expands, more space is created, which means more dark energy, which pushes things apart even faster. Creating more space, more dark energy, faster expansion. It's a runaway process. Over trillions of years, galaxies will drift so far apart that they'll disappear beyond each other's horizons. Stars will burn out. No new stars will form because all the gas will be spread too thin. Black holes will evaporate through Hawking radiation. Eventually, the universe will reach a state of maximum entropy. Complete disorder. Everything will be spread out so far and so evenly that nothing interesting can ever happen again. The temperature will hover just above absolute zero, and the universe will remain that way forever. Cold, dark, dead. This is the Big Freeze, also called heat death. The most likely end for everything. For 30 years, this has been the scientific consensus. The universe is doomed to a slow, lonely, frozen death. But in 2024, something changed. If you're still watching, hit that subscribe button, because what I'm about to tell you in part 2 could rewrite everything we know about the end of the universe. The 1998 discovery was so groundbreaking that Perlmutter, Schmidt, and Rees won the Nobel Prize in Physics in 2011. Their work fundamentally changed our understanding of the cosmos. But science doesn't stop. New telescopes are built, new data is collected, and sometimes that data reveals something unexpected. In 2024, the Dark Energy Survey released results from studying over 1,500 supernovae, the largest sample ever from a single survey. Initially, the data matched expectations. Dark energy seemed constant. But when they combined this data with other measurements, cosmic microwave background radiation, galaxy surveys, gravitational lensing, something didn't add up. It started to look like dark energy might not be constant after all. Like it might change over time. If true, this would be the biggest cosmological discovery since 1998, because if dark energy is changing, then all our models are wrong. And the fate of the universe is up for grabs. So scientists needed more data. A lot more data. They needed to map the universe in unprecedented detail. And that's where DESI comes in. The Dark Energy Spectroscopic Instrument. Installed on a telescope in Arizona, DESI is designed for one purpose: to test whether dark energy is constant or evolving. It can capture light from 5,000 galaxies simultaneously, and its mission is to measure the position and velocity of 40 million galaxies across 11 billion years of cosmic history. This is a massive international effort. Over 900 researchers from 70 institutions around the world, and in 2025, the first results came in, based on 3 years of data, with 2 more years to go. What they found is extraordinary, but I'm going to save that for part 2, because what DESI discovered doesn't just challenge our understanding of dark energy, it changes the entire future of the universe. So comment part 2, if you're ready to find out what happens next. And let me know, have you thought about how the universe will end before? Does the Big Freeze scare you? Or does it feel comforting that at least it's peaceful? The Curiosity Beast is all about exploring the biggest questions in existence. If you love content that makes you think about the cosmos and our place in it, subscribe, hit the bell, and join our community of curious minds. Because the universe's fate is being decided right now by forces we barely understand. and in part 2, we're going to explore what that means for everything. Thanks for watching, stay curious, and I'll see you in part 2.